Moving on, equilibrium. So we've done the two types of calculations, know them perfectly. Another thing that you'll see, as well as the definition for chemical equilibrium, dynamic equilibrium, reversible reaction, they'll always ask you this definition of le chatelier. So you've got to know this word perfect. And what it says is, when a system at equilibrium is subjected to a stress, the system responds in such a way as to minimize the effect of the stress. Hugely important. And what he means by a stress is anything that will affect either the concentration, the temperature, the pressure, the change in volume, or the presence of the catalyst. So applying this principle enables us to predict correctly the effects of changes in individual variables such as the following. So we'll apply this definition when we're looking at the effect of concentration on an equilibrium reaction. So equilibrium, you would have learned from junior cert, just meaning imbalanced. Don't write that in your chemistry exam. So the first thing we'll look at is looking at the effect of concentration on the position of the equilibrium. And what I mean by the position of the equilibrium, if we say that the equilibrium lies on the right hand side, we're just forming more of our product. Whereas if I say equilibrium lies on the left hand side, we're favouring the formation of our reactants. You're not going to get a high yield of your product. So we're looking at this, and this links into your notes as well. So if you look at your notes at Le Chatelier, you'll see there about your effects of these various stresses. So the first thing, if we increase the concentration of hydrogen, now I'm going to use my definition. If we increase the concentration of hydrogen, the system responds in such a way as to decrease the concentration of hydrogen. How is it going to decrease the concentration of H2? We're going to favour a formation of our products. So what we say there is equilibrium shifts to the right, favouring the formation of our product, hydrogen iodide or HI. So if we increase the concentration of H2, the system responds in such a way as to decrease the concentration of H2. How does it do this? Equilibrium shifts to the right, forming more of our product. So if we increase the concentration of hydrogen, the system responds in such a way as to decrease the concentration of hydrogen, always trying to keep it in balance, opposing, opposite. The concentration of H2, equilibrium shifts to the right, forming more product, and our product here, hydrogen iodide. We'll repeat that now for iodine. If we increase the concentration of I2, the system responds, look back up at your definition, the system responds in such a way as to decrease the concentration of iodine. How is it going to decrease the concentration of iodine? Equilibrium shifts to the right, forming more of our product, hydrogen iodide. Now, it's a reversible reaction, so it can take place in either direction. If we increase the concentration of hydrogen iodide, the system responds in such a way as to decrease the concentration of hydrogen iodide. How is it going to decrease the concentration of hydrogen iodide? Equilibrium shifts to the left, forming more of our reactants. So this is something that we can kind of learn off. Only in concentration will I ever say about the system responds in such a way. But learn this off, and it generally is up every year. So looking at this next point, if we increase the concentration of HI, the system responds in such a way as to decrease the concentration of HI. Equilibrium shifts to the left, forming more of our reactants, hydrogen and iodine. Continuing on with concentration, looking at this equilibrium reaction where hydrogen and iodine combine to form hydrogen iodide. If we decrease the concentration of I2, think to ourselves now using our definition, if we decrease the concentration of I2, the system responds in such a way as to increase the concentration of I2. How is it going to increase the concentration of I2? Equilibrium shifts to the left, forming more of our reactants. So if we actually decrease the concentration of this, we actually form more of this in an equilibrium reaction, in a reversible reaction. So if we decrease the concentration of I2, the system responds in such a way as to increase the concentration of I2. Equilibrium shifts to the left, forming more of our reactants, hydrogen and iodine. It's the same for hydrogen. If we decrease the concentration of H2, the system responds in such a way as to increase the concentration of H2. How's it going to increase the concentration of H2? Equilibrium shifts to the left, forming more of our reactants, hydrogen and iodine. And looking at the last scenario here, if we decrease the concentration of HI, the system responds in such a way as to increase the concentration of HI. Equilibrium shifts to the right, forming more of our product, hydrogen iodide. So if we decrease the concentration of HI, the system responds in such a way as to increase the concentration of HI. How's it going to do that? Equilibrium shifts to the right, forming more product, hydrogen iodide. So it's something we can kind of learn off. Now, there's other factors or other stresses, and we'll try and do maybe 2 others of these before the time runs out. Change in temperature. So we can determine from the heat of reaction value whether a reaction is endothermic or exothermic. So I'm just skimming down to this one, and I can see there my heat of reaction has a negative value, and once it has a negative value, that means that's an exothermic reaction because heat has been given out, and heat's a form of energy. If it had a positive value, it just means there that it's an endothermic reaction. So temperature plays, or temperature can dictate what way equilibrium is shifted. The way I always remember it, if we increase the temperature, we favour the endothermic. So if we increase the temperature, we favour the endothermic reaction. And an endothermic reaction, remember your delta H, or your heat of reaction, has a positive value. So if we increase the temperature, we favour the endothermic reaction. If we decrease the temperature, just the opposite then, we favour the exothermic reaction, and that means your heat of reaction has a negative value. So in this scenario here, hydrogen and iodine given as hydrogen iodide, they've given me my heat of reaction. Don't care what that quantity is, but it's a minus. So that means that this forward reaction is exothermic. The backward reaction then must be endothermic. And sometimes they write that as if it's, they might write it as 2HI, breaking down into my hydrogen and iodine, and they just said delta H, just the reverse, is equal to plus 12.6 kilojoules per mole. You know, so once I see there the delta H is minus, I know there that the forward reaction is exothermic. So my backward reaction must be endothermic. So if the temperature is increased, once I see increased temperature, I'm thinking endothermic, increase in endothermic. If the temperature is increased, the endothermic reaction is favoured. Equilibrium shifts to the left. There's my left hand side. Equilibrium shifts to the left, forming more reactants, forming more hydrogen and iodine. The temperature is decreased. The exothermic reaction is favoured. That's always the case. The exothermic reaction is favoured. Equilibrium shifts to the right. That's your exothermic reaction. Forming more product. Forming more hydrogen iodide. Catalyst. We'll keep battering on. Catalyst. Now how catalysts work. Catalysts alter the rate of a chemical reaction, but they're not consumed in the reaction. If they increase the rate of the reaction, they work by lowering the activation energy. So a catalyst, if it increases the rate of the reaction, it lowers the activation energy. Now, it increases the rate for the forward and the reverse reaction by the same amount. So it has no effect on the position of the equilibrium. It just means that equilibrium is reached quicker. So it doesn't affect the equilibrium. So no effect in concentration as the rate of the forward reaction increases at the same rate as the reverse reaction. Position of equilibrium does not change, but equilibrium is just reached quicker. Nothing really there. Pressure. Pressure only affects gases, gaseous reactions. And we know a gaseous or a gaseous reaction because of these subscripts. So they all have to be G's. If you see an AQ or an S or an L, then pressure won't have any effect on this. Another thing there about pressure, it only affects reactions when there's a different number of molecules on either side. So on the left here, we're looking at the Haber process in our production of ammonia, I can see there I have 4 molecules on the left hand side. I've got nitrogen there and I've got 3 hydrogens. So I've got 4 molecules in total. Whereas on the right hand side, my ammonia, my pyramidal shape, I have 2 molecules. So I have more molecules on my left hand side of the equilibrium and less molecules on my right hand side. So what you've got to remember is if you increase the pressure, you favour the side with a smaller number of molecules. I always think if I'm squeezing this down, there's not enough room for all these molecules, so you're going to favour the side with a smaller number of molecules, otherwise they're going to be squished. So you're squishing down the pressure, so you want the side with the less molecules. Then if you decrease the pressure, you can let them breathe, you can let them reproduce, you can let them expand. You're going to favour the side with a greater number of molecules. So that's what you remember. An increase in pressure will favour the side with a smaller number of molecules. So in this case, if we increase the pressure, equilibrium shifts to the right, forms more of our product. A decrease in pressure will favour the side with a greater number of molecules. But as I say, this only affects gases. So where there's different number of molecules either side, and only affects gases. If we go back to this reaction of your hydrogen and your iodine, I'm giving you a HI, say if they were all gases. Perfect, pressure might affect it, but there's 2 molecules on the left, 2 molecules on the right, so pressure will have no effect on this. Even if they were gases, they have to satisfy 2 criteria, different number of molecules either side, and all gaseous reactions. So if we increase the pressure, we favour the side with a smaller number of molecules. Equilibrium in this reaction shifts to the right, doesn't always shift to the right, forming more product, forming more NH3. That was just in this scenario. If we decrease the pressure, we favour the side with a smaller number of molecules. Always the smaller number of molecules. Oh, the greater number, sorry. If we decrease the pressure, we favour the side with a greater number of molecules. Equilibrium shifts to the left, forming more of our reactants, forming more nitrogen and hydrogen in this case. And then the last thing here is volume. I say volume is linked to your pressure because if you decrease the volume, you're automatically going to increase the pressure because you've got the same number of molecules in it. So if we decrease the volume, we increase the pressure. And therefore, if we increase the pressure, we favour the side with a smaller number of molecules. So volume and pressure are linked. If you increase the pressure, you decrease the volume. If you increase the volume, we decrease the pressure. And we favour the side with a greater number of molecules. I'm just going through a wee example quickly. Here I've got a reaction. I can see there delta H is minus. So that must mean that this forward reaction is exothermic. And then the backward reaction is endothermic. They're all gases. They've all got the wee G's. What would be the effect on the concentration of PCl5, in particular if we introduce more PCl5? So if we increase the concentration of PCl5, the system responds in such a way as to decrease the concentration of PCl5. So equilibrium shifts to the left. I'll write this roughly and run out of time, forming more reactants. If we increase the pressure, we favour the side with a smaller number of molecules. In this case, we've got 2 on the left, 1 on the right. So we have a smaller number here on the right hand side. Favour the side with a smaller number of molecules. Equilibrium shifts to the right, forming more PCl5. And if we increase the temperature, straight away I know increased temperature favour the endothermic reaction, which is the backward reaction. Equilibrium shifts to the left, forming more of our reactants, PCl3 and Cl2, therefore decreasing the concentration of PCl5. Now that's answered very roughly.